For this video on our case study of total air conditioning, we're going to talk about the actual air conditioning processes. And we're going to review psychrometrics in this as well, but if you are stuck on psychrometrics, go back and watch the previous video and then come back to this one. So the first air conditioning process we're going to talk about is the most simple, which is cooling. And this is on page 11-10 of your textbook. In order to do that, I'm going to draw some kind of conduit, some control volume in which my atmospheric air is going to pass. So I have some control volume here, some cylindrical control volume, and the atmospheric air is going to enter at state 1. And it's going to enter at state 1 with its associated properties. Its temperature, its humidity ratio, also known as absolute humidity, its relative humidity, its wet bulb temperature, and all of the other associated properties that I didn't list, and its mass flow rate. Remember that mass flow rate consists of its mass flow rate of dry air and its mass flow rate of the water vapor that's contained in that atmospheric air. Now, for the cooling process, I'm going to have some kind of cooling coils. And let's say these are the evaporator coils of a vapor compression refrigeration cycle. And so because they're very, very cold, they're going to draw heat out of my atmospheric air and out of my system. And we'll call that the rate of heat transfer from 1 to 2. So it's going to exit at state 2, this atmospheric air, at a lower temperature than it entered at state 1. Its absolute humidity, or its humidity ratio, is going to stay the same, right? I didn't extract any water vapor. I didn't change the mass flow rate of water vapor or the mass flow rate of air, so that humidity ratio is going to stay the same. But interestingly enough, my relative humidity is going to increase, and I'll expound upon that a little bit later on in the video. My wet bulb temperature for 2 is going to decrease. I'll show that on the psychrometric chart as well. It's a little bit easier to see there. And as I stated previously, your mass flow rates of your air and your dry vapor don't change at all. I haven't extracted any vapor or any air from the system, only heat. So let's take a look at this on the psychrometric chart, where I think it's a little bit easier to understand. And just before we do that, let's kind of review some of the psychrometric lines. I'm not going to cover all of them, just the ones we're going to need for this explanation. So remember, your vertical lines are your dry bulb temperature. Your diagonal dashed lines are your wet bulb temperature. The straight lines across are your humidity ratio. The curved lines are your relative humidity. And now in the green here, I'm going to put your comfort zone. If you're unfamiliar with any of these terms and you want to review that, go back and look at the psychrometrics video. So let's plot state 1. Let's say I'm at some temperature and some humidity ratio. Let's say I'm a humidity ratio of 20% and a dry bulb temperature of 37 degrees. I'm just kind of arbitrarily picking this. Now, I extract heat from that system, and my humidity ratio stays constant, and I'm going to cool to a lower wet bulb temperature. And this is what that looks like on my psychrometric chart. So I'm just going to follow a line of constant humidity ratio to my lower dry bulb temperature to state 2, and ideally you want to get state 2 within your comfort zone. Now you can see as I did that, my relative humidity lines, these are my lines of relative humidity, 20, 30, 40, these fanned out lines until 100%. My relative humidity increased, though my humidity ratio stayed the same, and that's important, so hold on to that. All right, next let's talk about heating. The natural progression from cooling is heating, and it's just going to be the same thing in reverse. This is on page 11-13 in your textbook. I'm going to draw that same control volume, that same conduit in which my atmospheric air is going to pass. I'm going to enter at state 1 at some cooler temperature with all its associated mass flow rates and properties. Now, instead of cooling coils, I've got some kind of heater wire. Let's say this is a space heater at some electrical line that's producing heat, or it could be the condenser coils of a vapor compression refrigeration cycle, and I'm taking heat from that hot coil, from that electrical wire, and I'm passing it into my system. So now I have heat transfer into my system, which is obviously going to increase the temperature. So I'm going to exit at state 2 at a higher temperature than I entered at state 1. Again, just like cooling, my humidity ratio stays the same. I haven't added or removed any vapor or air. Now in this case, the opposite occurs with the relative humidity. My relative humidity is going to decrease. My wet bulb temperature, the opposite is going to occur. My wet bulb temperature is going to increase, but my mass flows stay the same. Let's look at this on our same psychrometric chart. I kept those lines up there for your reference on what line is what. And let's say I start at some low temperature at some high relative humidity. So I'm here about 85% relative humidity. Looks like 10, 11, 12, about 13 degrees Celsius, maybe just below. And I'm going to add heat in order to get myself into the comfort zone. Now, just like with cooling, except obviously working the opposite direction, I'm adding heat, so my dry bulb temperature is increasing. You can see these diagonal lines. I start at a lower wet bulb temperature, so my wet bulb temperature has increased. My relative humidity has decreased, though my humidity ratio, again, has remained constant. Let's talk about next cooling with dehumidification. So let's complicate the process a little bit. Let's talk about what happens when we continue to cool until condensation forms. And this is on page 11-15 of your textbook. I'm going to draw a very similar conduit, but now you see I have one point of entry and two exit points. So I have this drain here at the bottom. And this is how this is normally indicated on a sketch of a cooling with dehumidification process. Now again, I have atmospheric air entering its state 1 with its associated properties and mass flow rates. And I have these evaporator coils again, some cooling coils from, let's say, from a vapor compression refrigeration cycle. And again, I'm going to draw heat out of my system from state 1 to state 2. In doing so, I cool it below its saturation temperature at that pressure, at atmospheric pressure. And now condensation forms. So that vapor that was in that atmospheric air, some of it is condensing and draining out of the system. So now that does that, I have some mass flow rate of liquid water, some fluid, exiting at the bottom of my system within my control volume. And this is liquid water. Its temperature is going to be the same as temperature 2, and it has its own respective mass flow rate, some mass flow rate sub F, or a fluid of the liquid water. Now it's going to exit state 2, the same with any cooling process, at a lower temperature than state 1. But now my humidity ratio is not constant. I have decreased my mass of vapor and therefore decreased my humidity ratio, and I'll show you this on a psychrometric chart in a second. My relative humidity has increased to 100%. Now that's interesting. I have to be at 100% to get dehumidification. I'll again show you that on the psychrometric chart in a second. My wet bulb temperature, like any cooling process, has decreased from state 2 to state 1, or 1 to 2, excuse me. And my mass flow rate of air is still constant. I haven't extracted any dry air out of the system, but now my mass flow rate of the vapor is much less because I've extracted some of that vapor as condensate that came out as my mass flow rate F. So conservation of mass here is very, very important. So let's look at conservation of mass. What conservation of mass tells me is that what goes in has to come out. So therefore, the mass flow rate of the vapor exiting at state 2 is equal to the mass flow rate of the vapor that came in at state 1 minus what was lost as condensation. And you may lose that intentionally. You want to dehumidify the air, like a dehumidifier you would put in your basement, for example, to keep moisture from building up if you live in a damp environment that would cause mold, etc., in your basement. Let's look at this on a psychrometric chart, and we're going to talk about the relationship between humidity ratio and relative humidity, and how that condensate forms and why you have to be at 100% saturation. It's the only way to extract water from atmospheric air is to actually cool it. So let's look at the process first, and I'll kind of explain a little bit more. So I just picked some state 1 at some temperature with some humidity ratio, and looks like a relative humidity of about 35%, a humidity ratio of about 14, and our temperature here is looking about 37.5. I'm going to cool, as I extract heat, I'm going to cool as my dry bulb temperature decreases. I'm continuing to cool until I reach 100% saturation, right? Because as I'm cooling, my relative humidity is increasing until I hit my saturation temperature. Now follow along this. Once I get 100% saturated, I can't be any more saturated. I can't be more than 100% saturated. So now as I continue to cool to my lower temperature, my new desired dry bulb temperature, I am now keeping a constant relative humidity of 100%, yet my humidity ratio, because I'm losing water, some vapor is condensation, my humidity ratio is decreasing. So I like to explain this in kind of a example in class. I think it helps students. So I'm gonna do it here to kind of help you understand humidity ratio versus relative humidity. So let's say I have some mass of dry air. So this is my mass of dry air flying around, and it's carrying a bucket, and in that bucket, it's carrying the water vapor. Now the humidity ratio is the ratio of the mass of this water vapor compared to the mass of the dry air. And so that's what your humidity ratio is. Your relative humidity is the ratio of the mass of vapor that's in the air relative to how much vapor the air could hold at that temperature, the mass saturated at that temperature. So you can see in this case my bucket's not full, right? So I'm at some relative humidity where my bucket's only 35% full, let's say, for example. Now as I cool, right, my bucket shrinks. My mass of vapor hasn't changed. My mass of vapor hasn't changed. My mass of the dry air hasn't changed. So my humidity ratio hasn't changed. And I haven't increased the vapor, but my bucket decreases. So as I cool, the water's affinity or ability to carry vapor decreases as it cools. So I like to think of it as its bucket shrinking. So now my relative humidity is increased because the bucket is more full, even though the mass inside it hasn't changed. And this continues until I get 100% saturation. So now I've cooled enough that my bucket is completely full, even though I haven't changed the mass inside in the bucket. The mass of the vapor hasn't changed. The mass of the dry air hasn't changed, but now my bucket's full because the bucket has shrunk. So now my relative humidity is increased. And now if I continue to cool and decrease the size of that bucket, the water has nowhere to go but condense and pour out of the top of the bucket. So I can never be more full than 100%. So my saturation is always 100%. And now because I'm losing water as condensation, my humidity ratio changes because this ratio of the mass of vapor to the mass of dry air has changed.